Hello, this is Dr. Dinesh Koli from SIRT College Bhopal Sales Group. And in this video, we will discuss about binary vapor cycle. Binary vapor cycle. So we will discuss here the binary vapor cycle, its schematic diagram, and its working on temperature entropy diagram. Now, as we know that the Carnot cycle efficiency, which is given as or written as T max minus T min upon T max. Or here the T1 is shown as the T max, T2 is shown as the T min. So here actually T1 is the heat source temperature and T2 is the heat sink temperature. So to increase the efficiency of the actual engine, that is to approach the Carnot cycle efficiency, because Carnot cycle efficiency, even it is the hypothetical cycle, but it gives the maximum efficiency. So we try to achieve this efficiency or to approach this efficiency. We follow the concept of Carnot cycle. The total heat should be supplied at constant temperature T1 and rejected at T2. This can be achieved only by using wet vapor and not by using superheated vapor. So here we can see the thermal efficiency depends on only higher temperature T1. Higher temperature, it is heat source temperature. The heat supply depends mainly upon this. Since the lower temperature T2 is fixed by the natural sink to which it is rejected, because as we in the condenser we use the cooling water where heat is rejected, so it's a temperature approximate, it is fixed, so we cannot change it. Now only the one parameter at which heat is added more, it is the T1, which is the maximum temperature. So the T1 should be maximum to the possible extent, and because the heat addition is done in the boiler, so we have to make our concern on that. The mercury vapor leaving the mercury turbine. Actually, in binary power cycle, what do we do here? We use the two cycles. One is called as the steam cycle, another is called as the mercury cycle. And because there are some drawbacks of the steam cycle, and also there are some drawbacks of the mercury cycle. So on the basis of that, we use the combined cycle in which we use the steam cycle as well as the mercury cycle. Because as we know that if we use only the steam as the working fluid, then there are some disadvantages of that, because in that there are some metallurgical conditions. The metals are subjected to wear only up to the temperature which is 650 degrees centigrade, not beyond that. But to achieve that temperature, because we want to give the more heat in the boiler, and the heat is given by the combustion gases which are produced in the combustion chamber of the boiler. So the pipes which are carrying the steam, they are subjected to high temperature as well as pressure. But the metal can bear only the temperature, maximum up to 650 degrees centigrade, but not the very high pressure. But the steam to which we are achieving maximum temperature, it is not possible only at the lower pressure. We have to attain the very high pressure. So this is the difficulty in that steam cycle. So we use another working substance, the mercury. But mercury is also having, because it is toxic in nature, uh, it is having the, it is doesn't debate the surface heat transfer is there. It's costly also as well as because of the limited supply. So the solution of this is to use the combined cycle using the both the cycle. The mercury leaving the mercury turbine is condensed because there is the mercury turbine and mercury boiler. So the mercury vapor which is produced by the mercury boiler, it is supplied to the mercury turbine, and after leaving the mercury turbine, it is condensed, and the heat released during this condensation is utilized to heat and evaporate the feed water to become steam. This is the concept from here, this condenser to the water. It means in the condenser of the mercury, the heat is rejected, and that rejected heat is utilized by the water or the feed water to convert it into steam. Now, this steam is then expanded in the steam turbine to produce work. Mercury turbine also produces work. The two fluids, mercury and water, are used in binary vapor cycle. It means there are two fluids which are used. One is the mercury and another is the water. Heat rejected by mercury is utilized by water in this cycle. So this was the theory part. Now with the help of this schematic diagram, it will be more clear to you. So here you can see a schematic diagram. So the two cycles are shown here. So first we will discuss about the mercury cycle. Here you can see this is the mercury generator. Okay, so mercury is there, but it is in the liquid form. So here the heat is added here in this mercury boiler. Heat is added, that is we can say QA. QA amount of heat is added here. At point A, the mercury vapor is produced, then this mercury vapor from this mercury boiler is transferred to this mercury turbine. Here you can see at this point A, the mercury vapor is produced and that mercury vapor is transferred or supplied to the mercury turbine. So this is the mercury turbine. This is the mercury turbine. Here the expansion of the mercury vapor will take place. This is the isentropic expansion. Okay. So from A to point B, the mercury vapor is expanded. After expansion, this arrow this way downward. Now after expansion in the mercury turbine, the mercury vapor, now here it will pass through this mercury condenser. Here you can see this is the mercury condenser. This one, the mercury condenser. So mercury at the very high temperature, it will pass through mercury condenser, because in this condenser there will be the heat rejection here. Heat will be rejected here from this mercury condenser, that we can say QR. But what is happening here? What is happening here? The mercury is rejecting its heat. Then here this heat is going. So you can see the water, feed water is coming and passing through this section, this mercury condenser. So the rejected heat of the mercury in the phase change is received by the feed water, which is coming from the economizer. So the water is getting heat here. So from 0.5 to 0.6, it is the part of the steam cycle, and this steam. Okay. So in one part we will see the mercury steam after passing through this mercury condenser will be condensed and it will become the liquid mercury. And with the help of the mercury feed pump, here you can see this is employed here a mercury feed pump. Now this mercury feed pump will draw the liquid mercury from the mercury condenser at point C, and then it will increase its pressure at point D. And then this liquid mercury is supplied to this mercury generator, or you can say mercury boiler. And again, this mercury boiler will get heat and then it will produce the mercury vapor. Then that will be further supplied to this mercury turbine, and this cycle continues in that way. Now, in the second part, we will see what is the steam cycle. So we have seen this part in the mercury condenser, the mercury vapor has rejected some heat. That heat utilized by the feed water. Now this steam will pass through the superheater. So actually, superheater here this mercury vapor will be superheated. So actually, this is also the part of the mercury boiler. There is no separate boiler is used for the steam cycle. In the mercury boiler, this superheated, and then this steam superheated. After superheating this steam, this is supplied to this the steam turbine. You can see here, this is supplied to steam turbine. This is the steam turbine. The isentropic expansion of the steam will take place in this steam turbine. Then after expansion, this steam will pass through this steam condenser where it will reject its heat, QR. will be take place here in this steam condenser. Then this will be converted from steam to the water, means from point 2 to point 3, and this water is then taken with the help of the feed water pump, and it will pass through economizer, and then it pass through the mercury condenser, and then it is superheater. So this cycle is repeated. Now here you can see electric steam generator. This is the electric steam generator. So the turbine work is which is turbine which is coupled with the electric steam generator. It produces power here. Also electric mercury generator. The mercury turbine also produces work. So in this way, we are getting the work from both the turbines. But the main principle or main concept, because in this condition, the mercury cycle operates at a very high temperature, and because it rejects heat at the high temperature, so the feed water takes that heat. So this is only the scheme diagram. Now we will go to the TS diagram for that. So first on the top side, you will see this is the mercury cycle. So you will see from A to B. A to B is indicating the mercury turbine work. This is the WT of the mercury cycle. At point B to point C, this is the mercury condenser work where heat is rejected. Heat rejection will take place here. This is QR. Now from point C to point D, this is the mercury pump work. Here you will see this is the mercury pump work. WP is there. Then D to A, the heat addition takes place in the mercury boiler. It is QA, heat addition in the mercury boiler. Then mercury boiler produces the mercury vapor at the point D, point A, and then it enters the mercury turbine. So this is how the mercury vapor is running across the cycle. For the second part, which is the steam cycle, consider this point 1. This is the condition of the superheated steam. Then 1 to 2 is the isentropic expansion of the steam along this path. And here we are getting the turbine work for the steam. At point 2, the steam enters the condenser where it rejects its heat. Up to point 3, the heat rejection here takes place in the mercury, in the steam condenser. And 3 to 4, you will see this is the steam turbine or steam cycle pump work, WP. And from 4 to point 5 and up to point 1, this is the heat addition which takes place for the steam cycle. So this is how the combined cycle or the mercury steam cycle is running, and in that way it increases the efficiency of the cycle. So we can obtain the more and more efficiency of the cycle by using the two working fluids. Thank you.